All right, ladies and gentlemen of chemistry, welcome to the mole. Talked about this a little bit in class, how a mole can be very closely related to a dozen. If I say I have a dozen cookies, that means I have 12. If I say I had 2 dozen, that means I have 24. It's a different way of representing the number of particles or the number of objects that you have. A mole works on the same principle, except for instead of saying you have 12, you're saying you have 6.02 times 10 to the 23rd cookies. That's a lot of cookies. Remember, this is 602 and 21 zeros after that. That's a huge number. It works the same for cars. But if we're going to be talking about moles of something, we're going to be talking about the number of atoms. If I have a sample of aluminum that's big enough to work with, like I can measure it, I can react it, it's going to have billions and billions and billions of aluminum atoms in there. This is a yucky number to work with. Anytime I have something like times 10 to the 23rd, that's hard to work with. It's hard to make comparisons and do math with numbers like that. It's easier to do math and make comparisons with numbers like 1 and 2 and 2.5, things like that. So scientists came up with a way of talking about the number of particles, like atoms or molecules, and use a number that's easier to work with, like 1, as opposed to 6.02 times 10 to the 23rd. Number's always the same, mass is different. We talked about this in class as well, looking at the jelly beans versus the candy when you're talking about the kids in the candy store, or the quail eggs versus the chicken eggs in a cluster. You abbreviate it MOL. Hey, that's a lot easier, right? Dropping that E. That's kind of silly. All right. Always have the same number of particles. So 1 mole of carbon, 6.02 times 10 to the 23rd carbon atoms. 1 mole of water, 6.02 times 10 to the 23rd water molecules. These are called representative particles. The smallest particle of any element is an atom, of any compound is a molecule. Here they have molecules in quotation marks because technically it's not made of molecules, it's made of ions. If you remember when we talked about the structure of ionic compounds, you basically have this many Na ions and this many Cl minus ions. The reason here that it's 6.02 times 10 to the 23rd of each is because in every 1 NaCl, I have 1 Na and 1 Cl. If these subscripts were anything other than 1, we would have to multiply this times the number of the subscript to figure out how many ions I would get. We're definitely going to get into that more as the days come on. Alright. Now, you can use Avogadro's number, 6.02 times 10 to the 23rd, as a conversion factor. It's going to look like this. A particle can be either an atom or a molecule or an ion. Conversion factors, remember, is dimensional analysis. We looked at this in Unit 2 back in first semester. If you've forgotten, don't stress. We'll refresh your memory on that one. So, here we go. Here's a question. How many carbon atoms are in a sample containing 2.50 moles of carbon atoms? So really we're trying to convert moles of carbon to the actual number of atoms. To do that, we need the equality. In every 1 mole of anything, there's 6.02 times 10 to the 23rd particles. In this case, it's atoms. So I have 2 choices for conversion factors. Remember, it's just a fraction where I take my equality and I make it into a fraction. I have to use either this one or this one. What's going to tell me which one I use is what I'm starting with. Remember, 2.50 moles of carbon is on top of this fraction because I can write it over 1. And so if it's on top here, it needs to go on the bottom here so that it cancels. So really, I'm taking this times this fraction here. I want you to pause the screencast for a minute and do that math and see if you can get the same answer that I got. Pause it and do that calculation now. Okay, so the answer is 1.51 times 10 to the 24th atoms of carbon. 2.50 moles times 6.02 times 10 to the 23rd over 1. So really you're just multiplying by 6.02 times 10 to the 23rd. Anytime you're talking about the number of particles, you should have a really big number, a times 10 to the type number here, not a number like 1 or 2 or 3. Because we're talking about actual atoms here, and there's a lot of them in a sample. Oh my gosh, the dramatic effect of that music is just crazy. All right, I want you to pause the screencast again. I want you to answer these 2 questions. options. You're choosing either A, B, or C. Pause it. Do those two problems now. Okay, your answers should have been, for number 1, C. This is half of a mole, 0.5. So you should have half of 6.02 times 10 to the 23rd, which is 3.01 times 10 to the 23rd. You don't half this number, all right? I can't take away some of those zeros when I'm taking half of a number, right? Half of 2,000 is not, 20, it's 1,000, so we got to go that route. Number 2, your answer is B. If I'm talking about the number of moles, it should be a small number, not a big number like this. If you got C, that's because you're doing order of operations wrong in your calculator. Bring in a question tomorrow and say, hey, I got C for number 2 on the learning check. Can you help me with my calculator? I'll be glad to show you how to make that work. If you do ever get a number like that and you're talking about the number of moles, automatically you should tell yourself, nope, that can't be. Moles have to be easier numbers to work with. That's why we have moles. That's why they invented it. And this number is 3 times Avogadro's number of 6.02 times 10 to the 23rd. Molar mass. Molar mass is the mass of 1 mole of any substance in grams, equal to the numerical value of the average atomic mass. We did this in part 3, or model 3, of the activity we did in class on block day. You're just taking the number from the periodic table and changing it from AMUs, which is what the mass of an individual atom would be, and converting it to grams by just changing the ending. We're not doing anything to the number. You're just flat out looking at the periodic table. Now you're going to see lots of different names for this. Molecular mass, molecular weight, formula mass, formula weight, gram formula mass, gram formula weight. There's lots of different things that you can call this, but we're going to use one term, molar mass. I only put this slide up here to let you know that if you see some other names for this, we're calling it molar mass always. Always, always, always. All right, learning check. Here we go. Pause the screencast for a minute and see if you can find the molar mass of bromine and tin. Remember, it's straight from the periodic table. Round it to the 10th place. Pause it. Go. Okay. Should have gotten 79.9 grams per mole for bromine, 118.7 grams per mole for tin. Now the grams per mole is important because it's the number of grams in 1 mole. That's what molar mass is. Right, to calculate molar mass, we did this in class as well in Model 3. If I'm taking CaCl2, 1 Ca from the subscript from the formula times its molar mass plus the 2 moles of Cl times its molar mass. So 2 times 35.5 is 70, or 71, excuse me, plus the 40.1 is where the 111.1 comes from. If I was doing N2O4, 2 times 14 plus 4 times 16, 92.0 grams per mole. You're always rounding to the 10th place, and then therefore your final answer should also be to the 10th place. So even if you get 92, add the 0.0. So we're sure that you kept track of those good old significant figures. All right. We use molar mass as a conversion factor, much like we used Avogadro's number as a conversion factor, going from grams to moles or moles to grams. This is probably the most important conversion I'm going to need you to know how to make. We're going to do this a lot, not only in this unit, but 2 or 3 more times throughout the semester. You're going to have to remember how to do this type of conversion. So here's an example problem. Aluminum, bikes, yay. 3 moles of aluminum would be how many grams? How much would that look like on a balance if I had 3 moles of aluminum? So once again, here's my equality. 1 mole of aluminum is 27.0 grams of aluminum. This comes from the periodic table. If you don't have a periodic table, get one. Find it right now, and you'll see that it's 27.0 grams for every 1 mole. Now, once again, I need to use this as a conversion factor. Which way do I put this into a fraction? Is the 27 on top or bottom? Well, here. 3 moles is on top here. I'm trying to get rid of moles. I'm trying to go to grams. So moles has to be on the bottom here so that they cancel. 3 times 27 divided by 1. Do that math really quick. Okay, grab a calculator, pause the screencast, do that math, see if you get the right answer. Pause it, do the math, go. Did you get 81.0 grams of aluminum? If you didn't, check your arithmetic. It just would be as simple as 3 times 27. So that is what we are doing to be able to figure out grams to moles. A very important conversion when we're trying to weigh something in order to count it.